Welcome back to ECE 501B. Homework number 8, which will be your last homework, is due Thursday. It's not your last assignment. Your last assignment is the project, which is due Sunday, and that's Sunday evening. Office hours this week on Thursday, I have been rebooked for my 11 o'clock, so I will be available at 2 o'clock on this Thursday. And our final exam is 2 weeks from today, which means we really only have 4 more lectures left in terms of topic material, and that also means that in a little more than a week you need to fill out your teacher course evaluation. That's due by the last day of class, which I'm thinking is 11:59 p.m. on that date. I'm not sure I would wait that long, but we will have a class meeting on the 10th of December, which is a Wednesday. And the teacher course evaluations, which are helpful for me, are due by that time. So we won't spend time in class. You'll need to fill those out online. What I want to do is spend this week finishing up the finite dimensional material, which is chapters 8, 9, and 10. Today we will cover material in chapters 8 and 9. Essentially we'll cover material in chapter 8, and the extension to the real vector spaces will be in chapter 9. Then chapter 10 will be Wednesday, the next time we meet. And that will finally get to determinants of a matrix. When the textbook says linear algebra done right, basically that's meaning let's delay talking about determinants until the very end, after we've sort of learned a lot about what we might know or learn about the general idea of vector spaces. And so that's why the title is what it is, because determinants are in the very end of the material. Next week we will get into Frank's, and if you haven't been reading that, you might look at that and start making the connection between finite dimensional and infinite dimensional in terms of vector spaces. And now instead of finite dimensional, now we have functions which are infinite dimensional in that context. And you can start applying these ideas, inner products, norms, etc., to those vector spaces, just like we've done it for the finite dimensional case. Today what I want to do is cover generalized eigenvectors, which we like eigenvectors because they make our matrix representation nice, which really means we have diagonal or block diagonal matrix representations of these linear operators. That really only is available when we have normal operators in a complex vector space, or if we have self-adjoint operators in a real space. And so when we have generalized eigenvectors, they may be needed when we don't have those scenarios. When we're dealing with non-normal, we might have to go to generalized eigenvectors, or when we have non-self-adjoint in the real case, we might have to go to generalized eigenvectors. We may still be able to diagonalize those operators in their matrix representation. But once we have talked about generalized eigenvectors, we can then start to think about multiplicities of eigenvalues, and that will allow us to then define a characteristic polynomial, and then the matrix or the operator on that characteristic polynomial, or the operator satisfies its characteristic polynomial, and that's the Cayley-Hamilton theorem. Then chapter 10 will get into the trace of a matrix and a determinant and the determinant of a matrix, but that probably won't come until Wednesday, the next time we meet. Let's now talk about this idea of generalized eigenvectors and why it's there or needed. And we could sort of build up to that point by saying, here's the basic idea. And now that we're in chapters 8 and 9, we have gone away from inner product spaces and actually returned to the more general vector spaces. We don't need inner products to be talking about these generalized eigenvectors, but we've talked now about spectral theorems, and these spectral theorems actually tell us that when we have self-adjoint operators, those have eigenvectors that form an orthonormal basis. Spectral theorems tell us that self-adjoint operators have eigenvectors that form an orthonormal basis. And in fact, when we consider the more general case, let's say, of complex spaces, we can actually loosen up this self-adjoint property. We can say the self-adjoint property can be relaxed to operators that are normal. And that means that the adjoint and the operator commute. So that's all we need to have the ability to have eigenvectors that form an orthonormal basis when we're dealing with complex spaces. If we have an orthonormal basis, that's really equivalent to saying that we can actually decompose our underlying vector space V into a direct sum decomposition of one-dimensional subspaces. So the above comment on having an orthonormal basis when we have self-adjoint operators is equivalent to saying that the vector space V has a direct sum decomposition in terms of one-dimensional invariant subspaces, where those one-dimensional invariant subspaces are the eigenvectors or the span of those eigenvectors. Each eigenvector spans these one-dimensional invariant subspaces. That's what an eigenvector is. It's an invariant subspace, which means we can write or decompose V as, let's say, U1 plus U sub 2 plus U sub n. Or these U's are actually subspaces that are spanned by vectors that lie in the null space of T minus lambda sub 1I plus the null space of the vector in T minus lambda sub 2I, etc. And these lambdas, the eigenvalues, are distinct. What we're interested in today is when we don't have this situation. But what about non-self-adjoint or non-normal in the case of complex vector spaces operators. We can make a few observations. If we now have an operator that's not self-adjoint or not normal, we may have an insufficient number of eigenvectors. Meaning we may not have n of those if our dimension of the vector space is little n, which means we can't decompose into this collection of one-dimensional subspaces. We can't decompose in a one-dimensional way, and we may not be able to diagonalize these operators. And what we want to do is actually generalize this concept. Since we like to work with nice operators which are diagonal, it'd be nice if we could get them as close to diagonal as possible. What we will be able to do is we can decompose as a slightly different decomposition where now these subspaces may not be one-dimensional. Let me say that we now are looking at the null space of t minus lambda sub 1I raised to the n plus the null space of t minus lambda sub 2I to the n, etc., down to the null space of t minus lambda sub m I to the n. And note that I am making a distinction between lowercase m, or Michigan, and lowercase n, Nevada. Here I'm saying that m is less than or equal to n, and n, Nevada, is what I'm assuming our vector space dimension is equal to. Just for future reference, I may be using another variable, little d sub I, and I'm going to define that to be the dimension of the null space of t minus lambda sub I to the n. And that little d sub I is the multiplicity of the eigenvalue lambda sub I. So d sub I, which is the dimension of the null space of t minus lambda sub I raised to the n, is the multiplicity of lambda sub I. We may not then be able to diagonalize these operators, but what we can do, and that's because we don't have a complete set of eigenvectors, what we will be able to do is create what are called generalized eigenvectors, so that we can nearly diagonalize these operators. And here's the definition. Suppose we are given a linear operator t on some vector space V, and lambda is an eigenvalue of that linear operator. then a vector, let's say lowercase v, in our vector space capital V is called a generalized eigenvector of T if T minus lambda I to the j v is equal to 0 for some non-negative j. So that is a strict inequality. You could, maybe it's cleaner, and I kind of like to just think of it maybe this way. J is greater than or equal to 1. So j is 1 or more. If you can find a vector v that lives in the null space of t minus lambda sub I to some j power, then that's going to be what we call a generalized eigenvector. And I think you should realize that with j equal to 1, that's what we've been calling an eigenvector all along. Let's now look at this by means of an example so that we start to see what in the world are we talking about, what do these generalized eigenvectors look like. Here is an example from the book. On page 165, where now we have a linear map T that's operating on a three-dimensional space, z1, z2, z sub 3, and let's say that that linear map now maps to z sub 2, 0, z sub 3. Now, in terms of review for the final, what are the eigenvalues of that map? Well, the eigenvalues are such that T of z, which is this right-hand side, needs to be some scalar of the original vector z, which if we apply that here, then we have z sub 2, 0, z sub 3. That's T of z, and that's supposed to equal lambda times z1, lambda times z sub 2, and lambda times z sub 3. It needs to be some scalar multiple of the original vector z. That's the eigenvalue-eigenvector relationship or equation. This leads to three equations. From the first coordinate, we see that z sub 2 is equal to lambda z sub 1. From the second coordinate, we see that 0 is equal to lambda z sub 2. And from the third coordinate, we see that z sub 3 is equal to lambda z sub 3. And we need those equations to be true. From the first equation, we want that to be true for all values of z sub 1 and z sub 2. What's that imply about lambda? Lambda needs to be equal to 0 if it's true for, well, running out of space, so let me say for all z1 and z2. Maybe what we should have done is looked at the second one first. This one now says if this is true for all z2, lambda is equal to 0. What about the third one? In order for z sub 3 to be some scalar multiple of z sub 3, for all z sub 3, lambda is equal to 1. we now have identified the three eigenvalues associated with this linear operator, 0, 0, and 1, and we don't have three distinct eigenvalues. So that already raises a flag and says, oh, we may have difficulties with finding orthonormal eigenvectors. Let's look at the eigenvectors in this case. And here, let me just define A to be the matrix representation of T, which if we go back here, that's going to be a square matrix. It's 3 by 3. And what's my top row of the A matrix? Now I'm saying that when I hit Z with T, I need to return the second coordinate in the top slot, which means that I need to pull that off with my matrix. So the top row will be 0, 1, 0, and that will give me Z sub 2 when I use this matrix times Z1, Z2, Z3. If I want to get 0, I hit all the vector components of Z with 0, and if I want to return Z sub 3, I simply pull off that third coordinate. That's the matrix representation of A, and now with that particular matrix, what are its eigenvectors? For eigenvalue equal to 0, we want to find the vectors that lie in the null space of A minus lambda I. Lambda is 0, so we're really just looking at A, which is 0, 1, 0, 0, 0, 0, 0, 0, 1. Or the null space of A minus lambda I with lambda equal to 0 says that I need 0, 1, 0, 0, 0, 0, 0, 0, 1 times this vector Z to map to the 0 vector. And again, this is going to give me three equations that I need to satisfy in order for this hopefully non-zero vector, Z1, Z2, Z3, to be mapping to the origin. From the first row, does that impose any constraints on the vector Z1, Z2, and Z sub 3? What's it impose? That was too easy of a question, wasn't it? You could have flipped a coin and gotten half of the answers, and I hope by this point in the semester your coin would have been two-sided, meaning it would have said yes on all sides on that question. So the first row tells us something that maybe it constrains some form of that vector Z, and in fact it's saying Z sub 2 is equal to 0, isn't it? If we just multiply it out. So for an eigenvalue of 0, we need the eigenvector to be such that Z sub 2 is equal to 0. That's from the first row of that relationship. The third row, which is also a non-zero left-hand or A matrix entry, says that Z sub 3 is equal to 0. And the second row doesn't tell us anything. It says 0 is equal to 0. It doesn't give us anything, but what do we know about Z sub 1? In order for this matrix, A times Z to equal 0, what does Z1 have to be? It can be anything, can't it? No matter what Z1 is, if that first coordinate Z1 is anything, it's not going to influence, it's always going to map to the origin. Now we know what the eigenvector associated with lambda equal to 0 equals. The eigenvector V is now spanned by 1, 0, 0. So we're 1/3 of the way for finding a basis of eigenvectors for our underlying vector space capital V. What about the eigenvalue lambda equal to 1? Now if we repeat that process, we need to compute A minus lambda I, which is just A minus the identity matrix, and A was, and it had a 1 down in the third 3, 3 entry, which now subtract a 1 from that. Here we have a -1, and here we have a -1, and I think that's now my A minus lambda I. We want to find vectors, non-zero vectors, such that they, when pre-multiplied by that matrix, A minus I, give us the 0 vector. So we're looking for vectors that live in the null space of A minus lambda I when lambda is equal to 1, or we now have -1, 1, 0, 0, -1, 0, and an all 0 row. The first row tells us that -z1 plus z sub 2 is equal to 0. The second row says that -z sub 2 is equal to 0. And the third row doesn't tell us anything, any constraints on the different coordinates. The first row, though, we could rewrite and say that z2 is equal to z1. The second row actually tells us that z sub 2 is equal to 0. Combining that with the first row's result says that z sub 2 is equal to z sub 1 is equal to 0. We now know that z1 and z2 are both 0 in the eigenvector associated with lambda equal to 1. And z sub 3 can be anything. And now we have the eigenvector V equaling 0, 0, 1, or something that is spanned by that. This is now normalized if we wanted to think of it that way. 0, 0, 1 is an eigenvector. For our second eigenvalue, lambda equal to 1. But now we're basically out of vectors, aren't we? And we need a third one. We only have 2 vectors in a 3-dimensional vector space. We need to figure out what's going on with that other eigenvalue, which was lambda equal to 0. What about the other eigenvalue at lambda equal to 0? And as I said before, when we first learned our eigenvalues, we sort of knew something might be problematic since we didn't have 3 distinct eigenvalues. And lambda equals 0 is repeated. But even with that repeated eigenvalue, we only found 1 eigenvector for that eigenvalue that was repeated. There was only 1 eigenvector associated with lambda equal to 0. We could say that another way, we could say, or the dimension of the null space of A minus lambda, with lambda being 0, times I raised to the first power, that was just one-dimensional. So we need to do something else in order to create or find another vector that we could use to form our basis for this vector space, three-dimensional vector space, capital V. And that's where this idea of a generalized eigenvector comes in. We need a generalized eigenvector to create a basis for V, which is three-dimensional. Well, based on what we had talked about before or defined with our generalized eigenvector, let's now look at the null space of A minus 0 times I to a higher power. Let's square that. That A minus 0I is just A squared. A was 0, 1, 0, 0, 0, 0, 0, 0, 1, and we can repeat that. I want to do the easy part. I'll do the second row. Second row just says scale all of the rows by 0. Take 0 times the first, 0 times the second, and 0 times the third. So the middle row better return 0. If I look at the top row on the left-hand side of that matrix product, that says just scale the second row by 1 in the second matrix, or the rightmost matrix, and the second row is all 0. If I scale that, then the top row becomes 0. And the third row in that product of A's says just copy or scale the third row by 1, and the third row in the second matrix is just 0, 0, 1, and I'm supposed to copy that. That's now what needs to be in this square bracketed expression. I want to now find vectors that live in the null space of this matrix. And hopefully this one is pretty clear that it has more than one vector that will lie in the null space of that matrix. We wanted it to be increased because just A minus 0 times I without a power was just giving us one-dimensional null space. If we now look at the null space of this matrix, I'm going to write it a different way. I can see that Z1 and Z sub 2 could be anything I wanted, and Z sub 3 has to be forced to be 0. And that's another way of describing this subspace that's actually containing the generalized eigenvectors for lambda equal to 0. So that's a compact way of really showing that since Z1 and Z2 can be anything in F, we actually have two vectors, or a two-dimensional subspace, that we have identified, and we could write that as Z1, 0, 0 such that Z1 is any element in F, direct sum decomposition with 0, Z sub 2, 0, such that Z sub 2 is any element in F. We already knew what the other subspace was. That was just Z sub 3. So now we have a way of decomposing this three-dimensional vector space. We now have one piece being Z1, Z2, 0, with 0, 0, Z sub 3, where Z sub 3 is any element in F. Where this first piece, again, is the subspace containing the generalized eigenvectors associated with the eigenvalues at 0, and the second piece or subspace is the subspace containing the generalized eigenvector for lambda equal to 1. So we now have a way of basically building up or accumulating eigenvectors, generalized eigenvectors, when we run into this sort of limitation of not having distinct eigenvalues or when we have repeated eigenvalues. One observation that we can make now that we're looking at different powers of t minus lambda I, if we have t minus lambda I to the j v equal to 0, can we say anything about t minus lambda I to the j plus 1 raised to 1 more power and then scaling v, or operating on v? That's 0, right? Because we now are just hitting the 0 vector with t minus lambda I. So this is also 0, since t minus lambda I to the j plus 1 v is equal to t minus lambda I times t minus lambda I to the jv, and this we were given was equal to 0, and now we just hit that on the left or operate on a 0 vector with some operator, and that's going to give us the 0 vector. And that now allows us to say that all generalized eigenvectors are solutions of t minus lambda I to the n v equaling 0, with little n being the size of our underlying vector space, capital V. So all of our generalized eigenvectors will solve this expression. One thing that we can remind ourselves of is that when we're dealing with complex vector spaces, what can we actually do to the linear operator, or how much structure can we sort of immediately impose on that linear operator? Remember, we can put any operator t in a complex vector space into some particular form. You remember what form that is? So we can put an operator into polar form, but now I'm looking for a nice operator, which now nice means as many zeros as we could possibly have. Ideally, it would be diagonal, but we can't do that in general, but we can for complex vector spaces, we can triangularize. So we can, no matter what the operator is, no matter what kind of structure it has, we can put it into upper triangular form. We can put any operator t in this complex vector space into upper triangular form. What do we know about what's living or present on the diagonal of that upper triangular form? What lives there? Those are our eigenvalues. That's one of the nice things about being able to find the upper triangular representation. The eigenvalues are on the diagonal. However, that upper triangular form or structure is usually not unique. And we can't sort of get rid of what's off the diagonal if we don't have enough eigenvectors associated with each of those eigenvalues. Meaning it's only diagonal, or can be put in a diagonal form, if we have enough regular eigenvectors, where regular now is not generalized, is what I'm meaning by regular. But unfortunately, in a generic operator, these eigenvalues might actually be repeated. And what we want to know is what happens when those are repeated, or what can happen. What kind of a representation do we have? So each lambda let's say is repeated a number of times equal to its multiplicity, which we were now labeling d sub I, where little d sub I is the dimension of the null space of t minus lambda sub I raised to the n, where I is equal to 1, 2, all the way up to our m different or distinct eigenvalues. and little n is the dimension of our underlying vector space, capital V. Let's look at an example of this relative to a sort of basic case in terms of this structure of being diagonal or upper diagonal. Suppose we now let the matrix representation of T be 5, 1, 0, 5. Here's an upper triangular matrix representation of some linear operator. Now, based on what we just said, what are the eigenvalues? We only have 5. I mean, 5 is the only eigenvalue. We don't have 5. We have lambda equal to 5. And it's actually duplicated, or its multiplicity is 2. So now if we check to find out about its eigenvectors and generalized eigenvectors, if we look at T minus 5i, here I should say the matrix representation of T minus 5i becomes what? If I subtract 5 off the diagonal, I have 0, 1, 0, 0. And what eigenvector will live in the null space of that matrix? We know that actually the second coordinate of the vector E1 has to be 0 based on the first row. And because of the first column being all zeros, the first coordinate in E1 can be anything, and let's just normalize it so that we get 1. And that's the only eigenvector associated with this linear operator T, which means that we now have to go to the idea of generalized eigenvectors. If I now square T minus 5i, what matrix does that produce? If I take that T minus 5i in green and multiply it by itself, depending on whether you want to multiply by rows or columns, if we now say, okay, this top row of that product will just be a copy of the second row, and the second row is all 0. The second row says 0 out all the other rows, or multiply the other rows by 0 and add them together. Now we just get the null matrix, or the 0 matrix. And now it's not too hard to find vectors that live in the null space. We could say E1, when scaled by that T minus 5i squared, will give us 0, and E sub 2, if E1 is 1, 0, E sub 2 can be selected to be 0, 1. Where now the dimension of the null space of T minus lambda I squared with lambda equal to 5 ends up being how big? 2. And that space is spanned by E1 and E2. So for that simple 2 by 2 case, E1 was actually the eigenvector, and in this case, E sub 2 is the generalized eigenvector. In general, in this case, our multiplicity of the eigenvalue 5 was 2, and our underlying vector space was of dimension 2. So if we just summed up all the multiplicities, we would get the dimension of our original or underlying vector space, and that generalizes.